Welcome back to Triomeet. Let's solve this question. The unit of length convenient on the atomic scale is known as an angstrom and is denoted by 1 angstrom equal to 10 power minus 10 meter. This is an important relation. 1 angstrom is equal to 10 power minus 10 meter. This is something that will come in most of the questions, and this is something that you need to remember, that 1 angstrom is equal to 10 power minus 10 meters. The size of a hydrogen atom is about 0.5 angstrom. So we've got that the radius of the hydrogen atom is equal to 0.5 angstrom. So the question is, what is the total atomic volume in meter cube of a mole of hydrogen atoms? So writing this in meter, it would be 0.5 into 10 power minus 10 meters using this. So the question is, what is the total atomic volume in mole of hydrogen atoms? So we know that hydrogen atoms are in the form of a sphere. And what is the volume of a sphere? Volume of a sphere V will be equal to 4 by 3 pi r cube. This is a constant. Pi value we know, it's 3.14. R is this that we have calculated. So value would be 4 by 3 pi into r cube, that is 0.5 into 10 power minus 10 the whole cube. This will give us the answer 5.23 into 10 power minus 31 meter cube. Now our question is, what is the volume in meter cube of mole of hydrogen atoms? So we need to write this in moles, right? In 1 mole of hydrogen atoms, what is the volume? So 1 mole of hydrogen atom contains Avogadro number of atoms or particles. Now this would be, so therefore our volume will be equal to V, this is the V value, into Avogadro number. So we know, calculate the value of the atomic volume, that was 5.23 into 10 power minus 31 into Avogadro number, that is 6.023 into 10 power 23. So this will give our volume to be equal to 3.15 into 10 power minus 7 meter cube. This is our final answer for this question. 2.17. 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liters. This is the molar volume. So the molar volume is given as 22.4 liters. In terms of meter cube, this would be 22.4 into 10 power minus 3 meter cube. Now, what is the ratio of molar volume to the atomic volume? So the question is, what is the ratio of molar volume to the atomic volume? What is this value? That is our question. Hydrogen atom, size of hydrogen is 1 angstrom. Why is this ratio so large? Okay, so the question here is, this atomic volume can be found, like in 2.16 we have solved how we have found the atomic volume with the same steps. So here the radius of the hydrogen atom is equal to 1 angstrom divided by 1 angstrom divided by 2, that will give us 0.5 angstrom. So now you have to calculate the atomic volume. Like we solved before, atomic volume, hydrogen atoms atomic volume is like the volume of the sphere. So we can use 4 by 3 pi r cube. It is 4 by 3 into 3.14 into 0.5 into 10 power minus 10 the whole cube. So we'll get the answer 5.23 into 10 power minus 31 meter cube. In terms of molar volume, moles, in terms of moles, we'll get multiply this by Avogadro number, that is 6.022 into 10 power 23. We get the final value to be 3.15 into 10 power minus 7 meter cube. Therefore, the ratio would be, so we've got the ratio to be molar volume value, that is 22.4 into 10 power minus 3 meter cube divided by 3.15, the atomic volume, into 10 power minus 7 meter cube. This will give us the value 7.1 into 10 power 4. Since this is a ratio, it does not have a unit. Let's solve question 2.18. So the question here is, explain this common observation clearly. If you look out of the window of a fast moving train, the nearby trees, houses, etc. seem to move rapidly in a direction opposite to the train motion, but the distant objects seem to be stationary. In fact, since you are aware that you're moving, these distant objects seem to move with you. So, consider a railroad. It's a fast moving train. The train is at position A. After some time, it will be at position B. It's a fast moving train. And then consider that there's a tree here. A nearby object, tree here, and a distant object, mountain, here. Now, from the window, this seems to be the line of sight, right? Line of sight is from the observer's eye to the object. When the train is at this position, when it's looking at the mountain, it's over here. Now, once the train has moved a distance, and if you look back at the, when you're looking back at the tree, there's an angle formed here. Did you observe an angle? There's an angle theta made towards the tree. There's an angle alpha made towards the mountain. We observe that the angle alpha is much smaller than our angle theta. The theta angle value is large. So for nearby objects, the angular position with respect to the observer is changing more compared to far away objects. That is, the theta value is large compared to far away objects. It's changing at a large value. So we notice that the objects nearby to us are moving in the opposite direction, or that the ones with large angular position seem to be stationary or even moving along with us. This has to do with the angle that you observed.